Okay, part D, the switch in the circuit below is initially open. While the switch is open, capacitor C1 has a charge of 10 microcoulombs and the second capacitor C2 is uncharged. The switch is then closed. So just after the switch is closed, what is the current through the resistor R? Okay, so we start off with C2 is uncharged and C1 has some charge built up on it. So we close the switch and we want to know what is the current that flows. So right when we close this switch, this capacitor is uncharged. So if there's no charge on it, then initially, so right when we close the switch, we can consider this capacitor to just be a wire. And so we have a resistor, this resistor and this capacitor just connected by a wire. And so the voltage across this, whatever voltage is across this capacitor initially is going to be directly across the resistance. So what we have is some voltage across our capacitor, and since we can ignore this capacitor just right at the beginning, we're going to consider the circuit to be this capacitor and this resistor in parallel, and so they have the same voltage across them. So the voltage across the capacitor is going to be the current through the resistor times the resistance. And so this current is the voltage across the capacitor divided by the resistance. And the voltage across the capacitor is the capacitance times the charge on the capacitor. Sorry, that's not true. So the charge is the capacitance times the voltage. The voltage is the charge divided by the capacitance. We have so Q over RC, and if you multiply that out, you get 10 microcoulombs divided by 2 microfarads times 100 ohms, and that is the current in amps. And so the answer is 5 volts. I'm sorry, 50 milliamps. 5 volts is the charge, so 50 milliamps. A long time after the switch is closed, what is the voltage across C1? So now what happens, we have this closed, so current starts to flow and charge will go from whatever was built up on this capacitor initially to be shared between both of those capacitors. So we want to know what is the voltage across C1. So a long time after the switch is closed means that no more current is flowing anymore through the circuit. Okay, so we'd have some voltage built up on each capacitor, but there's no current flowing anymore. And so there's no current flowing through this resistor, so there's no voltage dropped across that resistor. And so our circuit effectively, after a very long time, is just these two, C1 and C2. So they'll have the same voltage across them because they're effectively in parallel with no resistance in between. So we know that whatever charge was built up initially on this one capacitor is now distributed between the two. So the total amount of charge hasn't gone anywhere. So we have that some Q initial is Q final, the total charge that's built up, which will be Q1 plus Q2. So whatever charge we had initially, Q initial, is now distributed between some final charge on capacitor 1 and some final charge on capacitor 2. So this final charge on capacitor 1 is capacitor 1 times V final, and the charge on Q2 is C2 times that same V final. So these are the same voltages. And so we want to find this final voltage, V final. And so what we have, if we have an initial charge of C1 times V initial, then we can rewrite this and solve for V final. So V final is C1 V initial divided by, so we pulled out V final on this, so we get divided by C1 plus C2. And so solving this, V initial was the initial voltage across so we already knew the charge in C1. So instead of plugging in C1 V initial, this is just Q initial. So it's just going to be the initial charge divided by C1 plus C2. So we have, this is 1.3 volts, 1.43 volts. Okay, after the switch has been closed for a long time, how much total energy has been dissipated by the resistor? So we started off with some amount of energy stored in this capacitor. We moved charge through the resistor, so we know that we've dissipated some amount of energy. But now, finally, we'll have some amount of energy stored on this capacitor and some amount on this one. So we want to find how much energy has been lost through the resistor, and that will be whatever the difference is between our final energy and our initial energy stored on the capacitors. So we want to find E final minus E initial is the change in energy, and all of that energy will have been lost through the resistor. So E final is the final amount of energy on these two capacitors, which is 1/2 capacitance, say this capacitance of 1 times V1 squared plus 1/2 C2 V2 squared, where these are the final voltages. So we can, this is just E final. And we're going to subtract E initial, which was 1/2 C1 V initial squared. So E final, this is 1/2 V1 final and V2 final are the same. So this is 1/2 C1 plus C2 V final squared. And this is 1/2 C1 V initial squared. And so V initial was, let's see, the initial charge divided by the capacitance. This is Q on C1 over 2 microfarads squared. So this is the initial charge divided by the capacitance of C1. This is the initial voltage. And so now we know all these things. V final was what we found here, and the rest are just things that we know. So if you plug in numbers for all of that, the energy difference that you'll find is 17.86 microjoules. And so you get this by finding the final amount of energy stored between on these two capacitors and subtracting the initial amount. So that's the change in energy. So that must have been whatever's lost through the resistor.